All right, so here we're going to take a look at the concept of induction. Now, the idea here is, well, let's say that if we look at the powers of 6, 6 to the first power is 6, 6 squared is 36, 6 cubed is equal to 216, and 6 to the 7th is equal to 279,936. All right, now I could see that the ones digit here is always a 6, right? And I want to make the conjecture here that for every power of 6, right, for 6 to the n, the unit digit is 6. Right, now the examples that I've laid out here is not a proof. Right, I've listed just examples of the proof. Right, now I want to use induction to maybe prove this, right? The idea here is that this is ripe for induction. Right, and the idea here is that, well, if I know that 6 to the k has a 6, has unit digit 6, then I want to ask myself, what is the unit of the next power, right? What is the unit digit of the next power? Of 6 to the k plus 1. All right. Now, again, using powers of exponents is 6 times 6 to the k. Okay. Now, again, the idea is I don't really need to know what the whole value of 6 to the k is, but if I use here the previous thing here, that 6 to the k has a unit digit of 6, that's all I need to know here, that it's a unit digit, right? So whatever the last unit digit is there, right, I know that's going to be a 6 by my hypothesis here, and then I just multiply it by that other factor of 6, right? And that would leave me to believe that the 6 to the k plus 1 also has a unit digit of 6. Now, arguing in this manner, this is steps towards a proof, right? It steps towards a valid proof. Okay, now there are some things that we need to clarify before, right? Now, the idea here, what we're doing is a type of recursive reasoning. All right, so say, for example, here that the sequence, we have a sequence a sub n equals to 3a n minus 1 minus 2, right? This is a subscript n minus 1, and then take away 2, and then a0 is 5. All right, and I want to ask myself, is every term odd? Okay, well, here we check that a0 is odd. Here. So the question being posed is, every term odd? All right, so a0 is odd. If a sub k is odd, well, here, just to list a couple of examples here, right? a1 would be 3 times 5 minus 2. So that's 15 minus 2, which is 13. a2 would be 3 times 13 minus 2, 37. Okay, etc. Right? So at least, again, right, not a proof here, but I can see that, all right, this looks like a valid kind of conjecture here, right? And a reasoning that I'll take, so let's just say here, let's say a sub k is odd. All right, now what does that tell me about the next one? A sub k plus 1. So that would be 3 times the previous one, a sub k minus 2. But if I know the previous one is odd, I have odd times odd minus 2. Well, odd times an odd number is another odd number. And if I take away 2, I'm back to being odd. Right? An odd number. So it looks like here that I only need to make this argument here once. Right? Because k is just a general k. Right? Again, as long as I've established a starting point. Right? A0 started off as odd. Right? And then from there moving forward, all of the other ones had to be odd based on this type of formulation, right? This recursive definition for my sequence. All right, here is where that kind of analogy to the dominoes comes into play. All right, so I showed you a video from someone else who created this video. It gives a good explanation of what is going on here, right? The idea here is that when you set up these dominoes, right, it doesn't matter where you are along the way, right? As long as you know that this first one fell, that's going to push every single other one, right? So the 8th K one is anywhere along the way, all right? And what that means is that if you know this one fell, the next one is also going to fall, right? But what's kind of hidden there in the back is, well, this kth comes anywhere along the way, right? It's here, it's here, it's here. So it's telling us that all of them are falling, right? All of these cases are true, right? If you prove this general kth plus 1 case to be true, right? And that's the idea here, right? The idea is that here, this k case, whatever the premise is, right? You assume that it's true. It's true, right? And then if that is true, that leads for the next one to be true. Right? Now, if that happens, then that is essential for my induction, right? If I can show this, right, then any Pn is true for all n. Usually n greater than or equal to 0, right? We're talking about positive integers. It does not need to start at 0, but again, for the most part, here we do have our base case to be the 0 one. Is what's referred to as the base case. All right. Okay, so here's formally what we will be doing. All right, so the proof structure we have state step 1. State P sub n clearly. All right. Now, what that means is that you can order all of these cases, right? One thing that is that we have to recognize here is that this type of proof, this induction proof, works when we can order the cases, right, in some kind of order from smallest to largest, right? Or I guess just smallest, and then the next one is bigger. All right. Okay, step 2, the base case. P of 0. Right. Prove directly. This is usually you just plug something in. All right. Now, what this is that first domino, right? You want to show that the first domino falls. Okay, that one gets pushed forward here. And it's the distance part, right? Or really just that it's going to be true, right? And here is where the inductive step comes, right? Here's where we are using induction, right? Step 3, right? Let k be greater than or equal to 0, right? So it could be 0 itself, but again, right? We keep it general so that we show that it doesn't matter where we are, right? The next one is going to fall. Okay, and here is where the inductive case comes, right? I assume P sub k is true. Okay. In other words, this now becomes my hypothesis. And my conclusion is going to be, I want to prove that the next step is true. P of k plus 1. All right. So here's where the induction happens. Okay. And I guess here's where most students kind of get tripped up on this kind of step here, right? Because it seems, as you'll see, it seems like, right, almost like magic, right? But this is a rigorous mathematical process, right? And after we have proved that it is true, that pk plus 1 is true, then the step 4 is just a conclusion, right? So as we see, most of our work is here in step 3. Right, when we get to step 4, you just say, therefore, by the principle of induction, P sub n is true for all n greater than or equal to 0. Right, that's the last step, right? Our conclusion, right? Showing that something is true, right? For any value of k. All right. And again, as always, right? Let's remember hypothesis. It's an implication, right? P of k is my hypothesis. My conclusion is to prove P of k plus 1. Okay. All right. So here, in the next videos, I'll work through some common types of examples that are that lend itself well to induction.